Welcome back, everyone, to this week's algebraic graph theory seminar. This week, the speaker is Blas Fernandez, and he'll be talking about the 2y homogeneous property in distance-biregular graphs.
Okay, thank you, Sabrina, for the invitation and the introduction. So as Sabrina mentioned, I'm going to talk about certain properties in the well-known class of distance-biregular graphs. So the idea for today is I will present what is this property that we call the 2y homogeneous condition, that this is a combinatorial property that we study in graphs which are bipartite. And I will also introduce or quickly recall what is what we mean by the local distance regularity property of a vertex. And then we will mix all these two properties together to study 2y homogeneous distance-biregular graph. So let's start. So in this talk, every graph that I will mention will be finite, simple, connected, and more or less bipartite. So let's fix first some notation. So gamma will denote a graph with vertex at x. And for any two vertices, x and y, we mean the distance between them, which is denoted like this, by the shortest path connecting x and y. And given a vertex, x, the eccentricity of x is the greatest distance between x and any other vertex that we have in our graph. And it is usually denoted by epsilon of x. And for every integer I, we also consider the sets of all vertices which are distant I from x. And this is the set gamma I of x. And given two of these sets, gamma I and gamma j, the intersection of all vertices which are at distant I from x and j from y, it is denoted like this. And we observe that the collection of all these sets, gamma I of x, is a partition of the vertex sets that we call it distance partition relative to our fixed vertex x. So in this talk, as I mentioned, every graph is going to be bipartite. And so let's recall quickly what we mean by this. So we will consider a graph gamma, which are bipartite, that we will call y prime bipartite. So this means that the vertex sets can be partitioned into two sets, y in y prime, in such a way that every edge has one end in y and the other one in y prime. Whenever we have this, I will shortly call such a graph y prime bipartite. And so let's start with the definition of our combinatorial property that we call it the 2y homogeneous condition. So in order to understand this property, we need first to understand or to define an important scalar that we will compute using vertices of our graph. So we have a bipartite graph, gamma, which parts y and y prime. And we will assume that every vertex in our bipartition y has the same eccentricity, and this eccentricity is d, and this d is greater or equal than 3. Now we will fix an integer I between 1 and the eccentricity d. And we will pick a pair of vertices xy, where x is in our partition y, and y is a distance 2 from x, and so it is also in y. So we have our graph, we have our bipartition y, we pick two vertices x and y, x in y, and y a distance 2 from x, and we have an integer I which is fixed. And now we consider all vertices which are a distant I from both of them, a distant I from x and a distant I from y. And all these vertices are in these sets gamma I of x, y. And whenever we have this triple of vertices, x, y, and z, where x is in y, y is a distance 2 from x, and Z is a distance I from both X and Y, we define a scalar and we call it gamma I of X, Y, and Z. So we have a triple of vertices, and for each such a triple, we will define certain scalar gamma I. Okay, so how we will define it? So in case that we don't have vertices at distance I from both X and Y, this scalar gamma I is going to be 0. Otherwise, if we have vertices at distance I from both X and Y, this scalar gamma I will be the number of common neighbors of X and Y, which are at distance I minus 1 from Z. So this is a triple intersection now. And let's consider the very special case when I is equal to 1. So when Y is equal to 1, and what we have? We have our graph. We pick a vertex X in Y, and a vertex Y, which is a distance 2 from X. And so it is also in our bipartition Y. Since Y is a distance 2 from X, we have a common neighbor. And so this set gamma 1 of XY is non-empty. And we also observe that now we would like to compute which is this scalar. So this is, since this scalar, this set is non-empty, it will be the number of common neighbors of X and Y, which are at distance 0 from the vertex that we pick. And so we have simply say that we have just one number and this set. And so we can simply say that for every pair X in Y, Y at distance 2 from X, and Z at distance 1 from both, and this scalar gamma 1 is constant, is always 1. And we simply write gamma 1 equals to 1, because this number does not depend on the triple X, Y, and Z. And so now the question that we motivate to study this problem is the following. So we have a bipartite graph, and we assume that every vertex in one bipartition have the same eccentricity, and this eccentricity is greater or equal than 3. And we fix now an integer between 2 and d. And the question is when the scalar gamma I, that's we already defined it, is invariant across all the possible choices X, Y, and Z, where X is in Y, Y is a distance 2 from X, and Z is a distance I from both X and Y. Recall that when I is equal to 1, gamma 1 is always 1, so gamma 1 is invariant. So now the question is, under which conditions we will have that, for instance, this scalar is invariant under the action, under different choices of X, Y, and Z, which satisfy this condition. Okay, if this is the case, if we have that for such a graph, we have that all the scalars gamma I and does not depend on the choice of the triple X, Y, and Z for every I between 2 and the eccentricity minus 1, we will call such a graph 2Y homogeneous. So now we need to process all this information, and for that I will introduce some examples and how we can easily think about this property in a combinatorial way. Okay. Okay, so first let's consider a very basic example. For instance, let's consider a path, this path. This is an example of a bipartite graph. Every vertex, every red vertex here has eccentricity d equal to 3. And okay, and every blue vertex, the eccentricity of blue vertices are not the same. So we would like to consider our property and 2Y homogeneous, we need to consider this partition Y, because vertices here don't have the same eccentricity. And now we observe that every time if we pick a vertex x, then it's the only vertex which is a distance 2 from x is y, and these two vertices are already on the partition. So this means that for every x in our partition y and every vertex y a distance 2 from x, this set there's no vertex which is a distance 2 from both x and y. So this number gamma 2 is 0. So now this is an example. This is an example of a graph which is 2y homogeneous, where gamma 2, the scalar gamma 2 is 0. Okay, we are interested in some other cases in which this scalar gamma 2 of course is non-zero. But these examples satisfy all our definitions. So first, let's say some comments about our scalar gamma I in order to produce some examples. So remember that we have our partition y, we pick a vertex x in y, another one a distance 2 from x, and now we consider all vertices which are a distance I from both x and y. And since our graph is bipartite, we may wonder where is this set? It is in y or it is in y prime. So this, of course, it is easy to see that we will have that this set, it is in y whenever I is even. So we'll have this situation. And if I is odd, the distance that we pick is odd, then we will have that this set is in the other partition, y prime. So whenever we have vertices at distance I from both x and y, now to compute number of common neighbors of x and y, which are at distance I minus 1 from z, should be like this or like this. So for even I, we have that all these vertices are here in y, and now we need to count vertices at distance I minus 1, which are at distance, which are common neighbors of x and y. And similarly for I or. So this picture is not very useful or helpful. So we need now to process this information and introduce some bubbles or distance partition that will help us easily to compute this scalar gamma I of x, y, and z. And we will call these bubbles or this distance partition the intersection diagram of a graph of rank 2, because we will consider two vertices at distance 2, and we will define with respect to these two vertices certain sets of vertices. So we have again a bipartite graph, we pick a vertex y, and now for every pair of vertices x and y, where x is in our partition y and y is a distance 2 from x, we define these sets. Gamma ij is the set of all vertices which are a distance I from x and a distance j from y. And among all possible sets, we consider those which are possibly non-empty, and so the ones that they survive are all of these shapes. Let's say gamma I minus 1 I plus 1, gamma I, and gamma I plus 1 I minus 1. And here we denote it, we represent it in this diagram, where a line between two bubbles indicate the existence of possible edges between these bubbles. So for instance, if we have x here and y is here, here we have all vertices which are a distance 1 from x and a distance 3 from y, and so on. And we observe that, for instance, all these sets are all vertices which are a distance I from both, from x. So these are vertices which are a distance I minus 2 from y, a distance I from y, or a distance I plus 2. All these guys are vertices which are a distance I from x. So this diagram, it will be now useful to understand the number that we would like to compute. So we have now then, we will consider such a diagram. And now we are, of course, interested in those vertices which are at distance I from both x and y. Those vertices live here. And now we will define our scale. So whenever we have that this set is empty for every possible choice of x and y, we will define our scalar to be 0. And otherwise, if we have vertices here, what we are going to do is we are going to count how many common neighbors of x and y, so this means how many vertices here are connected with a path of length I-1 with a vertex. So we pick a vertex here, set, and we just count how many paths of length I-1 we have between the vertex here and vertices which are common neighbors of x and y. And this number will be denoted by gamma I of x, y, and z. So this is a more visual representation of our scale. And we will say that our graph, bipartite graph, is 2y homogeneous whenever for every I between 2 and d-1, all these countings are independent on the choice of x, y, and z. So we will have to consider these bubbles. And we'll just consider these bubbles to make this count. Okay. And let's see in more interesting example. So let's consider, for instance, the cube. We observe that this is a bipartite graph or bipartite distance-regular graph, if you know already what is distance-regular graph. And now we can consider a partition of red vertices and blue vertices. And let's pick first a blue vertex. Any blue vertex, now any vertex which is at distance 2 from the vertex that we pick. And now we will consider this distance partition that I mentioned before. And it seems that for every blue vertex that we pick, and for every vertex at distance 2 from the vertex that we pick, the picture is the same. And now we can easily compute the scalar, so every vertex has eccentricity d is equal to 3. So we just need to compute the scalar gamma 2. And to compute the scalar gamma 2, we pick the vertex at distance 2 from both these two guys. And we just count number of common neighbors which are at distance 1. And so this means for this vertex, common neighbors at distance 1 are just this. So, and for this one, it is just this. So this means that the gamma 2 is also equal to 1. And a similar situation is now what happens if we pick red vertices. If we pick red vertices, the situation is the same, so we can compute gamma 2 as similarly as before, and we also have that gamma 2 is also equal to 1. So if we consider the cube, then we will have that it is an example of two R homogeneous bipartite graph or 2B homogeneous bipartite graph. So this notion of 2Y homogeneous, of course, depends on the bipartition. But as we see here in this example, it is the same in which partition we pick, and we will see later why. Okay, so another example, it easily may be deduced with the following situation. So I mentioned that we would like to consider these pictures. So we have a bipartite graph. We pick vertex x in y, another one y at distance 2 from x, and now we consider all these sets, gamma I, and we are wondering about vertices which are at distance I from both x and y. So one possible scenario could be that for every possible choice x of vertices x and y, all these bubbles that we have here are all empty. And if this is the case, by our definition, then we will have that all the scalars gamma I are 0. And what may happen here? So if this bubble is empty, then by definition the scalar gamma d minus 1 will be 0. But in case that this bubble is non-empty, then this means that this vertex here has no connections there. So this means that every vertex that it is here is a distance, at this distance from vertex combinatorial of x and y, and this distance is not d minus 2. So this means that in any case, whenever all these guys are empty, we will have that the graph is 2y homogeneous, and all these scalars that we define are 0. And an easy example of this situation is, for instance, to consider cycles. So whenever we have a cycle of length 2d, every vertex has eccentricity d, and for every possible choice of vertices, of spread vertices, x and y are distant 2 from x, the picture that we'll have is the following. So this is our cycle. All these guys are here empty, and this vertex here is not connected to any vertex here with d minus 2 steps. So this means that when considered blue vertices, the graph is 2y homogeneous, but also if we consider the blue vertices, the picture is the same, so it is also 2y prime homogeneous. And here the particularity is that all these scalars, gamma I, are 0. So this is a situation that may happen, that of course we are interested in some other situations where these scalars, gamma I, are not necessarily 0. Okay, so and we may wonder if this is the situation that happens with the cycles is a characteristic set for the cycles in the following way. So if we have a bipartite graph and we assume that all these bubbles are empty, is it true that the only graph would satisfy our properties are cycles of even length? Okay, if we think a little bit, then we will see that this is not necessarily true. And for instance, to see this, we can consider the so-called, so famous Petersen graph, and let's replace every edge of the Petersen graph by a path of length 2. So instead of this edge, we will subdivide it, and we will replace every edge by the path of length 2. And then we will have now a bipartite graph where two partitions, blue vertices and red vertices. And now if we consider every red vertex and we consider this distant partition that I mentioned before, the situation is the following for every red vertex that we pick. So these guys here are empty. And so this is an example of a 2y homogeneous graph, where all these bubbles are empty, and this is of course not a cycle. However, now if we pick blue vertices in the subdivision of the Petersen graph, we will have that for every blue vertex that we pick and every vertex at distance 2 from the vertex that we pick, the distance partition that I define has the same shape, and this shape is the following. So now if we would like to check this 2y homogeneous condition for the blue vertices, we observe that it is not satisfied. And to see this, we just need to consider all blue vertices which are in this bubble. So for instance, if we pick those dark vertices, dark blue vertices, we observe that first, common neighbors of the vertices that we pick are those which are here, and they are always and there is exactly one vertex. And for this blue vertices, number of, so we have here a distance, we are at distance 4. This is gamma 4, 4. And we need to count for each vertex here how many vertices, common neighbors of x and y, we have at distance 3. So for this blue vertex, we have 1, and this is this guy. For this blue vertex, we have 1, and so this is one case. So this means that for these vertices, this scalar and gamma 1, 2, 3, 4, gamma 4, it will be of these vertices will be 1. But now if we consider these vertices, we need to compute the number of vertices, common neighbors of x and y, which are at distance 3 from these two guys. And we observe that the only common neighbor of x and y is this vertex, and this vertex is at distance 5, is not 3, so it's a distance 5. So this means that the scalar gamma 4 for these vertices is 0. So for some vertices, we have our counting is 0, for some others, our counting is 1. So we say that it does not invariant on the triple, so we say that our graph is not to be homogeneous. Okay. So then our main problem is once we understand this definition. So our main problem is the following. So we have a bipartite graph with partitions y and y prime. We will assume that every vertex in y has the same eccentricity, and this eccentricity is greater or equal than 3. And we would like to find necessary and sufficient conditions in our graph so that we have these two y homogeneous curves. Of course, that this problem in general it is too hard. So we will also try to solve this problem or make a progress in solving this problem with the further assumption that we have an extra combinatorial condition that it is the so-called local distance regularity of a vertex. Okay, so and let's quickly define what we mean by local distance regularity. So we have a vertex x. We consider this vertex has eccentricity small d. We consider all vertices which are distant I from x for every I between 0 and d. So this is this distance partition. Now we pick a vertex y distant I from x, and then we observe that this guy has three kind of possible neighbors: those which are distant I minus 1 from x, those which are distant I from x, and those which are distant I plus 1 from x. We count for each how many neighbors of each type we have, and we have these numbers: the I of xy, ai of xy, and bi of xy. And if this counting does not depend on the choice of the vertex y at distant I from x, and for every I, we say that our graph is distant regular around x, or the vertex x is distant regular. And we simply write these numbers: ai of x, bi of x, or ci of x. And these numbers are called the intersection numbers of our graph. So if we now consider a graph, we will say that it is distant regularized whenever every vertex has this property. And a well-known result by Goldstein and Taylor says that if we have a graph which is connective and every vertex has this property, then you just have two options. Either your graph is distant regular or your graph is distance-biregular. In the first case, in distant regular graph, your graph is regular, every vertex has the same numbers, the same intersection array. While in the second case, you have that your graph is biregular, you will have two balances, and intersection numbers, and two pair of intersection numbers, one for each pair of vertex, for each vertex. So we will have a bipartite graph vertices which are in the same bipartition have the same intersection numbers, vertices which are in the other have the same intersection number, but these two arrays, and they are not the same. So, and now our question or our problem is the following. We would like to investigate the two-way homogeneous conditions on graphs which are bipartite distant regularized. So this means that we would like to study or to analyze which are those graphs which are bipartite distant regular and two-way homogeneous, or distance-biregular graphs which are two-way homogeneous. And so this is like the possible scenario that we have. So we have here all graphs which are bipartite, where all vertices in Y have the same eccentricity. And among these graphs, we have all those which are two-way homogeneous. And among them, we have those which are also distant regularized. And we know that such a graph may be either distant regular or distant biregular. So we would like to now, to start to understand what happened in this red area that we have here. So let's first consider the case of the distance regular graph. So if we have a distance regular graph, all vertices have the same eccentricity, and they will have the same intersection array. So it is easy to see, as we see in the example of the cube, that if our graph is two-way homogeneous, then it will be two-way prime homogeneous with respect to the other partition, and the scalars are the same. So this means that whenever we have a bipartite distant regular graph, it really doesn't matter which partition we pick in order to compute our scalars gamma I. So, and because of that, we will simply say that our graphs are two homogeneous without considering the bipartition, because it is the same, it doesn't matter. And so now this graph, two homogeneous bipartite distant regular graph, are graphs which are really well known and studied in the literature, and they were classified by Nomura. And in the following theorem, we have the classification. So every graph which has this property, and it is distance regular, bipartite distant regular, is one of the following. And here we have, for instance, the hypercube, and when d is equal to 3 is the example that we saw before, or a Kalmar graph, or some graph of diameter 5. And the only infinite family is this one, which is for C2 equals to 2. And so now we understand two-way homogeneous and distant regular graphs were classified by Nomura, and we already know all of them. At least we have the classifications, and we can study if we want. So now our question is, what can we say about two-way homogeneous distance-biregular graphs? And we will now consider this case. So we will set some notation. So we have now a distance-biregular graph gamma, which has two partitions, y and y prime. Because our graph is distance-biregular, we have that every vertex in y has the same eccentricity d, and every vertex in y prime has some other eccentricity, and it is the same, and it is d prime. And we have this relation between d and d prime. Every vertex in y has the same degree, and this degree is p0. And every vertex in y prime has the same degree, and this degree is v0 prime. And we can also find and define intersection array for vertices in y and for vertices in y prime, and we will denote it by bi and ci and bi prime and ci prime respectively. And we have some relations between bi and ci as follows in each case, and similarly with bi prime and ci prime. And because of this relation, we can simply write the intersection array of a distance-biregular graph using just two rows Here we will write the valency and all the values of CIs, and the valency from one partition and all the values of these CIs. So the intersection array distance-biregular graph is, we will denote it like this. And if we would like to consider the two-way homogeneous condition in distance-biregular graphs, in the distance-biregular graph, we have two intersection arrays which are considered to be different. Then this means that we really need to consider the partition where we start, where we pick our vertex x, our initial vertex, in order to compute the scalar gamma I of x, y, and z. So it really matters. We really need to consider this definition. And as an example, we can observe what happened with the subdivision of the Petersen graph. From one partition, we observe that the vertex that's in the graph has this property, two-way homogeneous condition. But if we pick the other partition, then it is not a two-way homogeneous. So this property really depends. For distance-biregular graph, really we need to consider the partition. So now, again, which is now our main problem? Our main problem is, in the best scenario, we would like to find a classification of two-way homogeneous distance-biregular graph as similarly as Nomura did, but in the case of distance-biregular graph. Nomura did it for bipartite distance-regular graph. We would like to do it for distance-biregular graph. And okay, so we are considering the case d greater or equal than 3, but if we have a distance-biregular graph with d is equal to 2, then this graph is a complete bipartite graph, and we already saw that gamma 1 is always 1, so this is the case. This is a graph which is two-way homogeneous. So complete bipartite graph are graphs which are two-way homogeneous. So we will now consider graphs which are we have eccentricity d greater or equal than 3, and we will split this analysis into cases. In the case where the valency of vertices in y prime is 2, or it is greater or equal than 3. So let's quickly consider the case when it is 2. So in the case when it is 2, I need to recall what is the definition of a kappa G cache. So this is what we mean by a graph which has degree kappa, girth, length of the minimum cycle G, and this number of vertices which depends on kappa and G, which is given as follows. So what we call kappa G cache, it has different names in the literature as simply a minimal kappa G cache or a more graph. So in other words, what we would like to just consider is a graph with this property, which is distance-regular. This is what we need. And it is such a graph, we can prove that it is distance-regular, and where the intersection numbers can be expressed just in terms of the degree kappa and the girth, and depends also on the girth. And a result says that if we have such a case and if we subdivide it, then the graph that we obtain is a distance-biregular graph. And it is a distance-biregular graph with vertices of valency 2, because if we pick an edge and if we subdivide it, we will have vertices of degree 2. So the first small result is in the case when d is equal to 3 and we have distance-biregular graph with these partitions. So it is easy to see that vertices in y prime has valency 2, if and only if your graph is the subdivision of a complete graph, and the partition y is the set of vertices corresponding to the complete. And in the case when d is greater or equal than 4, we prove that this is equivalent to the case when all these vertices, all these bubbles here are empty. And this is, of course, a distance-biregular graph with vertices of valency 2, which are well understood because they were classified by Taylor and Mohar, and these are subdivision graphs of these caches, and our partition Y is the set of vertices of the original graph. So let's say that we have our classification for when a graph is 2Y homogeneous with vertices of valency 2. These are those graphs which are subdivision of these caches. And we need to pick as Y the set of vertices. So we understood the case B0 prime equals 2. So for B0 prime now greater or equal than 3, and let's say that this is more hard, and it is harder, and let's say at the same time more interesting. And to do that, what we did is, okay, we need now to use properties of distance-biregular graph, and we will use now the local distance regularity condition to compute certain number of vertices. So we will define certain scalar ei to I. So we pick a vertex x, a vertex, another vertex z, let's say a distance I from x, and now we count how many vertices here are a distance 2 from x and distance I from z. So in the similar setting that you probably know about distance-regular graph, so here we will define this scalar, and it will depend on y on the bipartition where we start. And using the properties of distance-biregular graph, we can prove that we can explicitly compute this scalar using the intersection number of such a graph. And this scalar, it has an expression that depends on the distance I. So for whenever I is even, we have certain value, and whenever I is odd, we have a similar other value, but it is independent on the choice of the vertices that we have. Okay, now using this scalar that we have, we will define another scalar, delta I, using the intersection numbers of our graph. So delta I is an equation using bi's and ci's for I odd, for I even, and bi primes and ci prime for odd integers I. And okay, so this has a combinatorial interpretation that I will skip for now. But what we prove is that in case that the scalar that we define is 0, this characterizes the case when the scalar that we would like to compute is invariant and it does not depend on the choice of the vertices. So what we have is that the scalar delta I, if 0, if and only if the scalar gamma I that we would like to compute is invariant, does not depend on the choice of the triple x, y, and z. And in this case, we can compute this guy, and we can express it just in terms of the intersection numbers. And of course, this is a local condition because this is what happened for I. Now, if we repeat this condition for every I between 2 and d-1, we will get a characterization or the 2y homogeneous condition and distance-biregular graph. And so, in order to, if you give me a distance-biregular graph, we know which are the intersection numbers, and to check that this graph is 2y homogeneous, instead of checking by the definition, which seems to be hard, we can simply check these equations, delta I, using the intersection numbers, and if all of them are 0, we will have that our graph is 2y homogeneous. If there exists an I for which this delta I is non-zero, of course, the graph doesn't have the desired property. So, and we would like now to understand which are these 2y homogeneous distance-biregular graphs. And okay, by the time that we wrote our article with my colleague Safet Penich, so all the graphs that we know that they are distance-biregular with 2y homogeneous, and satisfied here, satisfy the equality. Number of vertices at distance 2 is exactly the degree of x. And they have also balancing d equals 3, or b0 prime equals 2. So we were wondering, because of certain problems related with the Terwilliger algebras, we were wondering about the existence of a two-way homogeneous distance-biregular graph where this condition is satisfied. And of course, we have d greater or equal than 4 and b0 prime not 2. And so this is the problem that's for sub-problem that we would like to solve. And we were wondering about the existence of that graph, and we know that the smallest one should be, in the case d is equal to 4 with the smallest eccentricity. And so now we can, in order to consider this graph two-way homogeneous distance-biregular graph, and if we would like to classify, we can consider different scenarios, different values for the eccentricity d, different values for the valency b0 prime, or different values for certain other scales. So, and we were able to make a progress in classifying two-way homogeneous distance-biregular graph where d is equal to 3 and d is equal to 4. And I would like now to mention this, but I would be very quickly. And the following, so we have the following. So we are working with bipartite graph, and whenever we have a bipartite graph, instead of partition y and y prime, we can think about points and blocks. And we can think about incident graph of certain instance structure. So it turned out that, just to do faster, that if we have, so there are certain structures that we call 2D designs. So these are subsets, collections of points and blocks with very beautiful properties. And every 2 points, they must intersect in the same number of points. And we can also consider that every 2 blocks either intersects or in the same number of points, or they are disjoint and so on. So we have a collection of points and blocks with certain axioms or properties. And it's turned out that if we have the incident graph of a 2D design, which is quasi-symmetric with one intersection number 0, whatever this means, this is, in other words, a distance-biregular graph with vertices of eccentricity 3 and 4. And, okay. Okay, and then let's come back to this picture. So if we are considering graph which have eccentricity d is equal to 3, and if we now consider our intersection diagram, let's talk about points and block. When this graph with eccentricity d is equal to 3 will have the two-way homogeneous property. So for such a graph, we need to have that every 3 points that we pick, and these possible points, all possible triplets are of this shape. For every 3 points that we pick, they must intersect in the same number of blocks, and this number is lambda. And so this means that the incident graph of a 3D design is an example of a graph which is 2D homogeneous. And this is an example of such a graph that it is not necessarily distance-biregular, nor distance-regularity. But now if we ask for some nice property on the block sets, on the set of blocks, and these sets of properties that, okay, blocks intersection numbers are 0, and one of them is 0, we will have a quasi-symmetric design. And and we will have this classification that we will say that a graph is two-way homogeneous distance-biregular graph with vertices of eccentricity d is equal to 3, if and only if it is the incident graph of a quasi-symmetric design with one intersection number equal to 0. And it's turned out that these designs are already well known and classified in the field of combinatorial design, and these are designs which are related with the so-called Cameron's extension theorem, and these belong to 3 different families. So these are Hadamard 3 designs and these 2 families. So for this family, it is only known the existence when lambda is equal to 1, and it is not known the existence of such a graph or such a design when lambda is greater or equal. So for lambda equals 2, it is known that does not exist, but for lambda greater than 2, we don't know anything. And now this is an isolated example that we don't know, it is not known that such a design exists. But this is any of these, the incident graph of any of this quasi-symmetric design is exactly a 2-way homogeneous distance-biregular graph with d is equal to 3. Okay, so of course this graph or these designs are not a solution of the problem that we wanted to solve, or sub-problem that we wanted to solve, because we need to consider graph with d is equal to 4. And so after classifying the case of d is equal to 3, we move to the case d is equal to 4, so 2-way homogeneous distance-biregular graph with d equal to 4. And here the situation is more interesting and is really not that easy, let's say. So when d is equal to 4, we recall that d prime can be either 3, 4, or 5 in principle, but it cannot be 5, and so d prime can be simply 3 or 4. So we may consider 2 cases, d equal 4 and d prime equals 3, or d equal d prime equals 4. And these are the cases that we are going to consider. So, okay, so the first case, d is equal 4 and d prime is equal to 3, it is, okay, this is something that for now that I'm still needs to be written, but it is known because I prove it. So this graph with d equals 4 and d prime equals 3, we don't have examples of such a graph, and it is easy to see. So the idea of this is to consider certain relations with the intersection numbers and prove we found the contradiction. So now we move to the case when d is equal d prime equal 4. And in this analysis, it is harder, and so we will split the cases whenever C2 prime has different values. And this is because of the expression that we have for our scalars delta I. So delta I, as if you remember, is something minus something times C2 prime minus 1. And because of this I, we would like to consider different values of C2 prime. In the case when C2 prime is equal to 1, of course, this I will be 0. And so the expression that we have for delta I is very nice, and it's simple. And so in this case, we prove that a graph is 2-way homogeneous with d equal 4 and C2 prime is equal to 1, if and only if it is the subdivision graph of a complete bipartite graph KNN. And in this case, we can compute the scalars. So gamma 1 is 1, so but all the other scalars are 0, and we have a graph with the following intersection array. But of course, this graph is not a solution of the problem that we had with subset, because in this condition here we have equality. And so if we have a solution of this problem would be with C2 prime greater than or equal to 2. And this is the case that we are going to consider now. And we do some computations, which are the possible intersection arrays for such a graph. And the smallest one, this one, already known. It already exists in the literature, and it is in this paper by Delorme, where distance-biregular graphs were defined or considered for the first time, or one of the papers where it was considered for the first time. We found that it belongs to a particular family, and so we know that this graph exists. So let's such a graph, it will be an example of the graph that we wanted to find. And so let's say that's now our goal to solve this problem is we are in peace because we know at least one example of such a graph. And so, it has this distance partition. But now the idea is, okay, this is an example of such a graph, but we would like to find which are all those guys with D equals D prime equals 4, which are 2i machines with C2 prime equals 2 or greater than 1. And what we managed to do is like we were able to express all the intersection arrays of such a graph in terms just of the two parameters, C and S. So these are the values of C2 and C2 prime. So this was not easy, but we need to have too many computations, but we managed to do it. And now we just need to consider two cases, C2 prime greater or equal than 3, and C2 prime equals to 2. And again, these two cases, because of certain equations that we have, that they are, I will not discuss it today, but so I will present just the idea. So in the case C2 prime greater or equal than 3, we compute our scalar gamma 2. This is this guy here. And we compute this scalar gamma 3. And of course, these two guys must be integers. And so because of indivisibility conditions, we prove that this case is not possible. So 2i homogeneous distance-biregular graph with D equal D prime equal 4 and C2 prime greater or equal than 3 does not exist. So the only case that remains to consider is the case C2 prime equals 2. And in this case, our conditions are nicer. And we have that a graph with D equals D prime equal 4, distance-biregular with C2 prime greater or equal than 2. Then our graph is 2i homogeneous if and only if the intersection array is the following for certain number C greater or equal than 4. And in this case, we have these scalars, gamma 1 and gamma 2 are equal to 1, and gamma 3 is equal to C over 2. So now the problem is for which values of C we can construct such a graph. But this is another problem that I will leave for those of you interested in this topic. And so just to finish, I would like to mention that this intersection array were also important in some other. So we construct such a graph using that we consider this intersection array in some other paper that we authored with Sabrina. So we already have this intersection array from another combinatorial point of view, and we discovered that we also think we can also use this 2i homogeneous condition to discover to construct new distance-biregular graphs. And so for now, this is what we have. So we would like to find the classification of all 2i homogeneous distance-biregular graph. We already understand which are those with D equals 3, those with D equals 4, and somewhere in the future we would like here to fill this gap. my conjecture is that there's no such a graph. And so this means that all 2 homogeneous distance-biregular graphs that are the ones that I presented today. So all those with d equals 3 and d equals 4. But of course, this is still open because I was not able to prove it. But this is something interesting for the future. And so, as I mentioned, this is why I'm studying this. This is like, I'm interested in connections with Terwilliger algebras, and these graphs are natural examples of certain conditions that we would like to study, but I will not explain today. And okay, you mentioned Terwilliger, so I should mention that also we are organizing a workshop here in Slovenia in 2 weeks. And though, of course, those of you who are planning to attend, I guess that will come. But those of you who are not attending and maybe they are interested in the topic, there will be some talks that they will be by Zoom. So if you are interested, you can also join the conference by Zoom. So here is the name of the conference where you will find the website and probably the Zoom link. And this is everything that I have for today.
Thank you very much. Are there any questions?
I have one question. Yeah. Hi, Blas. Thank you for the great talk. So, for your conjecture on how the distance biregular graph has to have this diameter at most 4, and you believe that there does not exist any like 2y homogeneous that is diameter greater than 4. Like,
Yes.
where did that instinct come from? Like, do you know that the diameter cannot be that big, or is it just like a gut feeling?
Yeah, so this is a very nice question. So because of these equations that we have of this delta I, this is an expression which involves the number C2 prime. And we can prove that if this C2 prime is greater or equal than 3, then the diameter can be 3, 4, or 5.
Okay,
So
right.
for C2 prime greater or equal than 3, we already have these conditions.
Okay.
And so we just need to consider these 2 cases. And so, of course, because of these conditions, C2 prime equals 1, this case seems to be easy. And but in fact, the case C2 prime equals 2, it is the more challenging. If we think about distance regular graph, this is the case when we are considering the Hamming graph, and
Right.
which is an infinite family of diameter and big diameter. But in the case C2 prime equals 2, because we don't have this regularity, I'm not expecting to have infinitely many such graphs. So this is why my conjecture is that CB is equal to 3 or 4, but the proof is not so known, let's say. I have some.
Okay, thank you.
If there are no more questions, let's thank Blas again.